All right. Things are about to get a little crazy. All right. Now, I really believe this is going to be pretty easy to follow. I hope. Okay. That's kind of the goal. But this is kind of a higher level thinking situation here. We have the squeeze theorem once again said if you've got a function that's in between two functions or equal to all the time, like this black one here is in between the blue and the red all the time, then at a moment where the blue and the red converge and they're actually the same point, then the black one is kind of squeezed in and has to be the exact same thing, the exact same value, even though you may not be able to find the black one's value itself. And that's exactly what's happening here, because part A says, why can you not use the product limit law? I mean, why can't we just say, okay, this, the purple? Why can't I say the limit as x approaches zero of that times the limit of that? Well, that's fine for this, because this one right here, the first one is zero, but the second one does not exist. So that is an issue. All right, so we can't find it that way, but we can clearly see from the graph, it looks like all three of them are heading to zero. This is the graph of all three. I haven't said what the other two are yet. Well, the black one is here, and you can kind of see that it's heading to zero because it's squeezed in between these two. Where you're like, what two? Well, um, we're about to figure that out. Because here's the fact: sine's always between -1 and 1. When you graphed it back in pre-cal, and maybe even algebra 2, it was like bouncing in between -1 and 1. Boom, 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 boom. That's what it was doing. Well, then, so with this one, the one that we're trying to find, okay, so any sine function, as long as it's not multiplied by something, any just regular old sine function, doesn't matter what's in here, is going to bounce in between -1 and 1. Okay, it does. That's what they do. So if we use that fact, this fact, leading to this fact, and then multiplying by x squared all the way across, and you're like, why x squared? Well, that's because of that. Just multiply by that all the way through. And here's what you have. So you'll have negative x squared is going to be less than or equal to x squared sine 1 over x, which is also going to be less than or equal to, because they can be equal to each other, positive x squared. Now we're here. All right. So the positive x squared is the blue graph up here. The negative x squared is the red one. And the black one is bouncing in, back and forth in between those two. Boom, 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 boom. Hey, good special effects. Sound effects. Sorry. Okay. So, all right. So this is a fact then. So now then, so the squeeze theorem says, okay, well, these two, if they have the same limit, that'll be the limit of this one. So that's how we do it. So we're going to say the limit as we are using x approaches zero of x squared, negative x squared, is equal to the limit as x approaches zero of positive x squared. All right. And then by the squeeze theorem, and by the way, those are both equal to zero. So then, therefore, hey, a little shortcut notation for therefore, not making this up. Therefore, a little triangle of circles there. Therefore, by the squeeze theorem, and really we could say this, like since this and those three things, since those are all true, by the squeeze theorem, woohoo. All right, so therefore by the squeeze theorem, the limit of the middle one, the one that's literally in the middle all the time, always in between or equal to, of x squared sine 1 over x is going to also equal what those other two equal, because they're all heading to the same place. Okay. Ooh. Done. Smiley face. Okay, now, all right, let's try one fresh then. All right, so, oh, it's at the same feel. Okay, but we'll pretend like we don't know that. Okay, so here's the thing. Here's what we know. So, a fact is that the cosine of any angle is in between 1 and negative 1, and also equal to 1 and negative 1 at times. Okay, remember your cosine graph was a little different, right? It started at 1. I'm saying start by hits the y-axis at 1, and then bounces between 1 and negative 1 forever. Okay, on both sides. Okay, so if this is true, all right, then that also implies, that negative x squared. Nope, not there yet. Not there yet. All right, that implies that the negative 1 is going to be less than or equal to any cosine. In this case, we were talking about 1 over x squared. So 1 over x squared in between negative 1 and 1. All right, now we go. All right, so then I can multiply across as long as it's going to be by something that's positive, that nothing that's going to change the relationship. And so the thing I'm going to multiply everything by will be x squared. So I'm going to multiply by x squared all the way across to all three parts, and we'll have this fact. So that leads directly to the fact that negative x squared. Okay. That leads to the fact that negative x squared is going to be less than or equal to x squared times the cosine of 1 over x squared. And that will be less than or equal to positive x squared. Oh man, so we're about to write the exact same thing that we did above. Okay, so since I like this, since this is true, and same thing we did before, the limit as x approaches 0 of negative x squared is equal to, it's kind of like the bread on this sandwich, and we know that the x squared cosine 1 over x squared is squeezed in between those two pieces of bread. So that's equal to 0. Also, the right hand side, I mean the upper part, sorry, upper piece of bread, not right. We know that by just direct substitution. So that's true, comma. Therefore, okay, by the squeeze theorem, all right, by the squeeze theorem, the limit as x approaches 0 of x squared, this is a crazy one, but we're able to do it. It's really cool. Cosine of 1 over x squared is also equal to 0. Boop, boop, boop. I don't know what that is.